Welcome to Kellis Coder. Today we will implement a basic implementation of forth in Zig. So go forth and multiply. I like that. Except I don't even have kids, at least not that I'm aware of. But I've been a guitarist, so... Just the other day I heard a soldier's falling off. Some Indonesian junk that's going round. Mommy's alright, daddy's alright, they just seem a little weird. Surrender, surrender, but don't give yourself away. Hey. Hey. Yeah, you may wonder what Cheap Trick's surrender has to do with writing forth in Zig. Nothing. But I also make these videos for me to learn new things. Zig, for example. But in this case I wanted to explore large language models and specifically Claude. And I have to say that Claude was really working himself in a sweat on this project. Because he implemented 90% of these forth immediate words for me in Zig. And that's quite an accomplishment. The compiled words he was a bit useless at. And at a certain point, writing forth, I was like, write me a binary 16-bit printing routine. Give it the whole specification. He was, sure man. And he does that and it's terrible.
Come on, Claude's just another lost quest.
So I asked Claude, are you guessing after like 5 or 6 attempts? And he's, yeah man, I'm totally guessing man. I was like, okay, analyze the problem and tell me. And he goes like, well, I see man that you implemented the roll word, which is not standard forth, but in the absence of I is basically the index if you do a do loop, a for loop. I took that out. It wasn't part of old forths. You can do that on the stack, but that made this problem really complex. And he was like, well, maybe that will work. And eventually I ended up doing it myself. So Claude reminded me of this stoner of one of my all-time favorite movies, Over the Edge, which by the way was the first movie that Matt Dillon did. And ironically, Matt Dillon auditioned because he wanted to skip school. And he got the role, never intended to be an actor. So that's a nice little tidbit of knowledge there. And Claude is my favorite character in this movie. He's basically the stoner. He's a good-hearted kid. So yeah, hence Cheap Trick, because that is one of the songs that plays in this movie, Surrender. So if you're my age, so born in the 70s, you probably really like that movie. And it has been an influence also on Nirvana, because Kurt Cobain's striped knitted vest or jumper, sweater, was influenced by Claude in this movie. And Richard Linklater's Dazed and Confused, another great movie that you have to watch, is influenced also by Over the Edge. And hence this little weird link. So let's jump in and have a look at the code. So I implemented a basic forth in Zig. And I broke all the rules that usually apply for writing an interpreter. Because usually you have a 4-stage approach. You have your lexer, which actually takes the individual tokens, finds those. Then you have your parser that will take those tokens and create them into token objects. Then you have your AST, that is basically a tree to implement and interpret these. And then you have the interpreter that goes through the tree and actually executes them. That is quite a convoluted way of building stuff, but it is the proven way to build an interpreter. But forth was developed with the mindset that the language should be so simple that you do not need that approach. You can actually just parse out every individual word and then reinterpret that. And I was like, I can actually do that. And let's go a step beyond that. I will even get rid of what I think all fourth implementations have. That is an operation stack, a word stack. I was like, yeah, but then I also have to keep track of program lines because, of course, this is a line and that is a line then. And, well, the until needs to look back to this word, so that line, etc. I was like, yeah, there's too much work. I can do it without that, for sure. I regretted that later on because certain things, like indeed the repeat until, became a bit more complicated without that. But yeah, it is the most minimal way to do fourth. So let's first build this and let's see how big the size is, because size matters. And people say it doesn't, but it definitely does. Because I may want to run this on a Pi Pico, for example, at a certain point. And then it needs to be small. So let's build it small. So not for speed, but for size. And let's look at this. How big it is. I get out the ruler. And it's 137 inches or kilometers. 137 kilometers long. Right? That's actually relatively small for an interpreter with so many interpreted words, because these are the words that are interpreted. It's pretty significant amount, right? But we can strip her. So let's play some strip poker and strip her and see what she will take off. 115k, so she basically took off her blouse and her skirt. Oh well, but it is smaller. It is significantly small. Now, if we start this, it will actually fail. Let me show you. It will complain that it cannot find the system.h, and later on, if it's not there, the user.h. Now, what I do is I have the system.h, which are basically system words. So you have your basic, immediate, and compiled words, and you build them up into more complex fourth words. So to-dub is a dub-dub, to-drop is of course a drop-dub, to-over is over-over. I actually never used the to-over before. Don't know why I implemented it. And then the user words. Now I do not have a save word. Usually I have a save word. It's toaster, toaster. That's usually when the waffle iron crushes my testicles. I have not currently implemented it because it's a minimal viable product, but it will be easy to implement an immediate word to save all these words to this standard file, because this file lives right next to the binary. So let's link this right next to the binary, because that way I can keep my source code in the source and have the binary right next, have those files right next to the binary. Am I in the right directory? Yep. So let's link them. Source, user.f, and system.f. So now they're right next to the binary. Okay. So if we go up and we do a clear and we will run forth, it will actually start. And it's perfectly happy. We can do the infamous 12 plus 13, pop it from the stack, and that is 25. Yay! Now my REPL loop, this is the REPL, it's more like a cripple loop than a REPL loop, because it can only read until the end of the line. Where is it? Here. So it reads these files till the end of the line. So if you have, for example, a multi-line approach, it would be nice to actually write it this way. That's currently not implemented, because why? It doesn't give me any extra benefit. Besides, it forces me to write small, readable words like this. Right? So, but we can add that later on. That's not the difficult thing, but it would just add a lot of clutter, especially for this video, because I started this as an instruction video for this channel, and then found some purpose for it actually. And the same here in the REPL loop itself. This is that while loop. I type in a command, and I will actually call my fourth interpreter and lex that line. And lexing is basically doing the lexing, parsing, and interpretation. And it's a maximum of 1 kilobyte. I've never had a word longer than a kilobyte before. So yeah, it's a REPL loop, but it's a rather cripple REPL loop. Now there was something that really tripped me up in this. You want to be able to catch a signal interrupt, a Control C. Because if you have, for example, a word like this, 10 print, it will repeat until I do Control C. And that Control C needs to be found. Let me show you that word actually. Here it is. It's a repeat begin. So that is basically a while 1 in C, right? So that is that Control C really needs to happen. I tried to implement this using the idiomatic Zig way, and there is this standard.os.darwin, and it doesn't exist in 0.13. So I asked my buddy Claude, I said, Claude, dude, yeah man, can you find the Darwin implementation? Yeah man, it should be over here, right? Let's do it like this, man. And I'm like, yeah, but it says it isn't found. Oh, then use the standard.linux, dude. And I use the standard.linux with the signal, and it compiles, I run it, and it crashes. And I'm like, yeah, that's probably because the ABI of Darwin is different from the ABI of Linux, so that will not work. I looked all over, I could not find a Darwin implementation. So then I resorted to what Zig is actually built for, interoperability with existing C. So I create a lightweight namespace called C, and I include my signal in there. And then I set up my signal interrupt with the pointer to my signal handler. And that is here. So as soon as I do Control C, I call the fourth interpreter, which is a pointer to the interpreter. Here I call it fourth, as to make clear that I'm actually doing fourth interpretation, and here I call it sigint, it's just the same pointer, but that I'm actually controlling the system itself. So if you have, for example, compiled words repeat, and the reason why these are compiled words is, if we look at this, if I have a repeat, this stuff, until or the begin, is reinterpreted. Same with a do loop. So this iterates 16 times. This is reinterpreted. And some implementations actually compile it on bare metal, which is kind of difficult in a protected operating system to actually generate code on the fly. You would need to do a lot of meddling with ownerships of memory, so didn't bother with that. Right, but that's why they are called compiled words. So that is the signal interrupt, and we have that here. We have the break flag, of course, when you have that until that we saw here. When it is 32768 equals, then it will actually do the, what was it? It will set the break flag, so it will signal to the repeat loop. This is what I meant with I took out that operation stack, so I need to pass stuff via a pointer to actually signal to stop execution of a loop. And here the same with that signal int if you press Control C. Those are, in my opinion, two different ways to terminating it. Control C is a hard way, and the until that actually sets the break flag is the software way. Right, okay, so that was something that I needed to figure out after I ditched the whole idea. I don't want an operation stack, which would in that case make these sort of things a bit easier. But yeah, this works. And since it is a structure, my lexer, sorry, this file. Since it is a structure, it will basically have that in there as well. So I can instantiate multiple instances, even if I wanted to make it multi-user, and still not have that interact, because it's not global in the sense that it is part of the main, but global in the sense that it's part of the interpreter. So if I want to run 4 jobs, which most forth allow you to do, you just instance another interpreter. So yeah, we're reading the files, we have the basic loop. So let's have a look at the lexer, because that is where the magic happens. This is the whole lex, interpret, AST loop. It's really simple. It looks like a lot of code, but it's actually not. We take in that line, so that is the line of code, and we just iterate character for character through that line. So first I start by stripping off extra spaces. So if we have 12, is my stack empty? Yeah. If I have 12, a lot of spaces and another 12, it will still actually strip these out and only keep 1. If it is equal to the end of the line, then we know that we're definitely doing something wrong, and then we break out. Could be a syntax error, for example. And otherwise, we find the position of the current end token. So 12 is a token in this case, but also do is a token. And I find the end position so that I can actually carve out that word from the beginning and the end. So that's basically what we do here. And that will become the token text, or the token. Now here we have something, a bit of a weird construction. Something I overlooked actually. Because forth is basically case independent. Most for things use uppercase. But if and my forth can actually do this, I can do a loop without a word, which I find very convenient, to be honest. So if I do this, sorry, other way around, 5, 0, do. See, I even have basic error handling in there. Not a lot, but I have basic error handling in there. Right, so we loop through that. And this is lowercase, but I can also do this, do dot. Well, dot doesn't have a case, of course, and loop. It will also work. I forgot the space there, but you get the gist. Now with the, if I put some stuff on the stack, with the dot s, I print the whole stack, say this is the amount of numbers and this is the stack. If I do dot s, I print the value from the top of the stack, 123 in this case. And if you do dot, you actually pop it off the stack. That case, so I ignore case by just lowercasing every token, and you will actually see that here as well. They are all lowercase, except for the only exception, the dot s capital. I wonder why they didn't choose another word for this, to be honest. But yeah, so I'm like, okay, in that case, I will uppercase it. I could have used the add mem copy. Well, it looks a bit weird, right? It looks a bit out of context, so hence I use that here. But that's really that whole block. And then we just go through the words. So we have those dictionaries set up. Here we go. I have my stack. That is the argument stack with my stack operations. Just a struct. Great stuff in Zig. And my dictionary. And I have 3 dictionaries. I have the user words. That is what we saw here. Then I have the immediate words. And then I have the compiled words. Right? Those are 4 hashes. There are hashes. So these are my dictionaries, and I initialize them here, and I fill them in during the initiation of the lexer. So I will check the user words if the current token is in there. If it is in there, I will capture the value, because the get token, if it is in the if and you capture the value, actually gets the value. And then I just pass it recursively into the lexer. So I call the lexer to actually lex this word, because it will actually return this whole statement. It's really that simple. And the compiled words, well, these are actually function pointers. And this goes back to one of my first videos. If block and case block must fucking go. You see a lot of interpreters and other applications with loads of case statements or loads of if-elses. Why just create a bloody function pointer like I have here? This is for the immediate words, that's the definition. It's a constant function pointer that takes in an interpreter object and a compiled function, since we need that whole line of code and the position. It's a constant function pointer that takes in the interpreter, the actual line of code, and the current position pointer. And we just put them on the bloody structure, on the dictionary, and then we can call them. And that is what we do over here. Like, if I find the word in the dictionary, then I get the value, and the value is the function pointer, and I just take that function pointer, put in my arguments, the current arguments, and it will run that. And similarly, and even more easily, the immediate words, it just puts itself on there and executes that function. And it's also wickedly fast, because these are hashes, of course. If there are not any of these words, then it must be a stack value. So if I have a stack value like right, so it says, okay, this must then be a stack value. I check if it is a number, and if it is a number, I will parse it as a float. And that's one of the cool features about my version of Forth. I can actually add float numbers. So if we look at the stack, here we go. Right? So the check number also includes the dot, that it's a valid character. And if it's valid, if it can actually do it, it will actually parse it out and add it to the stack. If not, then it's not a valid word. So if I do this something, it says, this causes an invalid word, because it's not part of the dictionary and it's not something it can interpret as a floating point value. So yeah, that is the whole loop. You just iterate through it, and each token you either call the function pointer, or you send it to the interpreter. And if it's a compiled function, it will indirectly, recursively call the lexer function. And this is something that you could actually write in assembly as well, because this is really trivial to write in assembly, except for, of course, the dictionary. I would use, in that case, probably linked lists or jump tables, and that is basically a case statement. But the case must go. If you have a higher language, that is, then the case must go, then you just use a dictionary. So this means it's really easy to extend this language. Just the other day I was like, I implemented the Night Rider scanner, and it goes so quick, I need a millisecond timeout. So I just create a word millisecond with the function implementation of millisecond, and just add it here, which is basically a sleep that I need to, of course, cast from the float value of the stack. And this is where Claude really came in. I mean, Claude is amazing. Claude did all the hard work here. Yeah, you're allowed to sweat, Claude, buddy. You did all the hard work, and I will admit it. And this is when I started to see the value of LLMs. Usually LLMs create fucking crappy code, especially in Python and JavaScript, because it goes around the normal distribution. And there's so much crap code in Python and JavaScript, because it's such an easy language, noobs actually use it. So 99% of the time you get the worst crap code out of that bell curve. Zig is a new language. There's not a lot of stuff on GitHub that it can actually learn from. So the results are actually really, really useful. Just like, as I said, with actually getting that location of the exe file, that Claude actually read really, really quickly.
I just did some speed up work.
To get that self-exe path alloc. Because there's not a lot of junk in its learning database. So when I started implementing these words, I'm like, oh, this is so tedious. This is so frustrating. This is where I usually stop projects, my own projects. For a client, it's like, I get paid by the hour. I'm fine with this. If you want me to do tedious jobs, I can do them. But for my own, just like video games, when I need to grind, I'm like, I'm fucking done with this shit. When I'm not getting any reward of it, then... But in this case, I was like, okay, let's do a shift bitwise. And Claude actually was like, oh, because it's context aware. So if I do this, then you probably will do this. Yes, I want that. Oh, and then I will pop those things from the stack. And, well, I know what a shift does. And I know that it has this operator. Boom. And all I had to do was just check if it was correct. Run it actually on the CLI. And yeah, that is good. Because sometimes order matters, especially with minus and division. So yeah, Claude actually amazingly did 90% of this. I'm not kidding you. Even the .cap s, he basically filled that out. Like, okay, you want to print the whole stack? Well, it did not do the makeup the way that I wanted, because I wanted, of course, to also have the length in there, so I put that. But yeah, 90% of this, it's Claude's work. Claude really was tripping here. He definitely was on speed. He definitely was flashy, man. Wow. Yeah. Compiled words, no. Because these are very tailor specific to my situation. Ugh, I see I want an empty line there. So this is basically all me. But yeah, they're just a handful. I believe the print string was something that it came up with, based on the context that I wanted the outward. Yeah, but yeah, the compile words, especially since I also need to jump over, set the end pos to something that beyond the end word, as I call it. So the begin or the do and then the repeat, or the do and the loop. Yeah, so that is the implementation. It's really easy to now extend it and add more functionality. And that's the whole idea about Forth. That's the Forth mindset. So let's have a demo. We're already in my cripple REPL loop. So let's see what I implemented. These are some words that I implemented. Here I have the word black, brown, words that you're apparently not allowed to use anymore. But let's do a brown, black, red, and then the word resistor. And the word resistor calls resistor in ohms. So that's the recursive part where I call the lexer recursively. And then it will call resistor in human readable form. And that is a 1K resistor indeed, yes. If you do a brown, red, and this is where my floating point, of course, shines, it's a 1.2K resistor. If I do a yellow, violet, brown, that should be 470 ohms. That is 470 ohms. So it evaluates here with these if statements, whether it's mega ohms, kilo ohms, or just ohms. Right, then I implemented the word yellow with text colors. The text color came later on. So if I do yellow, my prompt is nice and yellow. But I can also do a 31, for example, text color that should be red, I believe. Yep. So I can do text colors. We already seen this, I believe, the 10 print with the Ctrl-C demo, that Ctrl-C works. So basically your Commodore 10 print, hello, semicolon, and that is what that loop does. So that is my test loop. But then with the colors implemented, I wanted to have a random function. So I implemented a random function later on that takes the begin and the end value, and these are inclusive, and it will just put a value on the stack, which then the text color consumes. So if we run that, you can already predict what is happening. We get different colors, baby! Woohoo! And it goes so fast that it actually is dithering the colors, because these are the actual colors. There are not that many, there are 8, right? Yeah, there are 8. And then I did something. I need to clear a bit of screen for this. Because usually if you use Forth, you tend to use it in an embedded system. So you will use GPIO. And the thing that I always do, my hello world for GPIO is the kit scanner. I have no hardware here implemented that has a GPIO. I was looking for that Velleman kit that I soldered about a year ago. I don't know where I put it, because otherwise I would have linked in that USB library and actually implemented the hardware word. But maybe later on I will do it on the PyPico, because I think with a little work I can actually compile this for the PyPico. But here goes the kit scanner. It actually puts it on a fixed location, also using ANSI terminal. So I have 27, that's escape, emit, and then I print the open square bracket 10 semicolon 10 F, and that prints it to a fixed location, and it's scanning left to right. Now I have to do a very embarrassing admission. This word took me 45 minutes to write. I was like, Claude can actually do this. So Claude, yeah man, write me a word that prints out a 16-bit value in binary. All right, dude. And it wrote something because I knew that this was going to be a hassle with all the stack orders, and I don't have variables implemented. If you use a variable, it's easier because that persists. I have not yet implemented it. Would be easy enough. Probably would have been quicker than actually figure this out. But yeah, so Claude came up with something. Yeah, dude, this should do it, man. And I put in a value 65535, expected to be all ones, and I go like, Claude, they're all zeros. Oh, I see the problem, dude. Let's do this. So Claude, the last case that he is, did something, and it's still all zeros. I'm like, it's all zeros. Oh, try this. So after about the 4th or 5th attempt, I was like, Claude, you're guessing, right? Yeah, man. Actually, he said, yes, I'm guessing. And I'm like, stop guessing, analyze the problem. And he's like, sure, I can do that. Or, sure, man, I can do that. Just give me some extra weed, man. And he says, much to my amazement, because I had already forgotten about this, yo, man, you implemented the role word. That will be a lot easier to handle, because it started also with using the I. I, by the way, is something that they fill in the do loop. It's a relatively new addition in Forth. A relatively new addition, I mean the 90s or something. I did not implement that because then I would need another global variable to find it, and you have I, J, K, and need to count the number of depths to fill in. I was like, nah, I can just use the stack and do that. So I told him not to use the I, and he got lost. So he was guessing. But then he said, oh, you have the roll statement, and you can just roll it. And so, well, sure, yeah, that's a good idea. I totally forgotten that I implemented roll. And he's doing it, and it's still all zeros. So I said, Claude, it's still all zeros. Oh, man, I know how to fix it. And he actually did this. And I'm like, if I type in 128, it will give all back zeros. Yeah, that's because the else is also a 1. You need to put in the zeros. So he was tripping by that time. And then I sat down, and in like 20 minutes I figured out the order of all these operands. And in total it took me 45 minutes for something as trivial as writing this. And I know I could have used Zig, because Zig has a perfectly valid print binary function, but I wanted to implement this in Forth just to show the capability of this Forth. Man, we can actually see 16 bin, what's it called? Bin 16. And it will spit out the whole word, so I can actually iterate over the words call C and write them to a file. But yeah, I have not implemented yet the save words, and I don't really see a value because I tend to edit it in here anyways, and then start it and check it. Yeah, so this is where we're currently at. So it's really simple just to add new words, extend it, and Zig is bloody great. And Claude, I mean, he may be a stoner, but he's become my best friend. And I don't know if you know Claude. I say watch the movie Over the Edge. You will, if you're my age, you will definitely love it. Didn't I see you crying? Didn't I see you lying? Didn't I see you loving, see you crying? Didn't I see you crying? I want you to want me. Yeah. Cheap trick, it's quirky, just like Fourth, just like your boomer and silent generation parents. But, you know, mommy's alright, daddy's alright, Fourth is alright, and Zig is fucking brilliant. I really adore Zig. I had a great time actually manhandling Claude every now and then to get stuff the way that I wanted it. And it was a learning experience how to prompt these LLMs. I will not ridicule them as much as I did, to be honest. It does make certain things really convenient as a developer, like the tedious stuff. Now, you know, the stuff that you know that you can read and see, like, okay, this is good or this is bad, and those are the things that you don't really like to program anyway. So yeah. So Fourth in Zig, it's definitely very cool little project. Link in the description. You can extend it to your own wishes. And I'm curious what people will do with it. If not, then I still had a great time working with it. And see you in the next one.